Okay, now let's read the problem together. Okay, so this BMC company is trying to ship some cars from uh, ports in Newark, New Jersey, and Jacksonville, Florida, to some locations, distributors located in Boston, Columbus, Atlanta, Richmond, and Mobile. Okay, and this figure shows the possible shipping routes available to this company along the transportation costs, along with the transportation costs for shipping. And currently, there are 2 cars available at the port in Newark. Okay, so as we said, this negative number here represent the supplies. Okay, same as here. So 300 are available in Jacksonville. So this negative 300 means supplies. Later we'll talk about why do we use the negative values here. Okay, but here we'll just continue. So in this problem, node 1 and node 7, these 2 are the supply nodes. Okay, then let's look at, is there a demand node? A demand node means that node only has inflows. Okay, for example, here, this node 4 here, it has 3 possible ways to receive cars. Okay, but there is no flows that goes out from it. Okay, so this is a demand node. So this one is demand node. So let me put it here. So the supply nodes are 1 and 7. Okay, and we have 1 demand node, which is number 4. Okay, so we look at number 2. Number 2 has a route that goes in and 1 goes out. 3 has 2 goes in, 1 goes out. 5 has several goes in and several goes out. 6, 2 goes in, 2 go in, and 1 goes out. Okay, so all the other ones are, we call them transshipment nodes. So 2, 3, 5, 6. So these are all transshipment nodes. And these arcs that connect those nodes, we differentiate them as, for example, let's look at node 2. Okay, this arc that goes into it, we call it an inflow. Okay, and this arc that goes out of it to node 3, we call it an outflow. So this is a inflow. This is an outflow. Okay, we're going to use these inflows and outflows a lot in our constraints. Okay, so now let's look at this problem. Now they have 2 nodes with a total of 500 supplies. Okay, and they are going to transport those 500 supplies to 2, 3, 4, 5, 6. Okay, here at Boston, which is node 2. Okay, it has inflow and outflow, and it has a demand being 100. So what does that mean? Regardless of the number that goes into it and goes out it, as long as 100 units stay there, then Boston's demand is met. Okay, think about this again. So we don't care whether it's 200 units goes in or just 100 goes out. As long as what goes in subtract what goes out, is meeting this demand of 100 here, then we fulfill the demand at Boston. Okay, then it's the same for node 3. There is one inflow from node 3, okay, sorry, from node 2, and there is another inflow from node 5. So another inflow could come from, say, 7 to 5 and 5 to 3. Okay, so we have two inflows to node 3 and one outflow back to 5. Which when the problem is solved, this may not, these two arcs will not have value greater than 0 at the same time. Okay, it does not make sense. Okay, but when we put a constraint, we have to consider this. So, and back to what we talked about, like for node 2, as long as what goes in to node 3 subtract what goes out from node 3 is fulfilling this demand of 60 here, then we are meeting the demand for node 3. Okay, so this is just some brief analysis. And so let's first define the decision variables. Okay, and the decision variables, we define them in the same manner as what we did in chapter 3 in that transportation problem. Okay, we just because that's what we're trying to decide, how many cars to ship from one node to the other. Okay, so our decision variable will be xij, the amount being shipped from node I to node j. Okay, just for example, x12 means the number of cars shipped from node 1 to node 2. Okay, so with this, we have our decision variables, and for all the transportation, all the network problems, this is the general way that we define the decision variables. It's always xij using the subscript to represent the from node and the to node. Okay. So next, so we have our decision variables. So the decision variables are xij, number of cars shipped from node I to node j, and I goes from 1 to 7, j goes from 1 to 7 too. Okay, then our objective function. Objective function is to minimize the cost, right? Which is very similar to the problem that we talked about in chapter 3. So regardless of how many cars you're going to ship on those routes, we want to minimize the total cost. So it will be to minimize. So and the one thing you need to pay attention is don't miss any of those arcs, especially those between those two nodes. The direction is the routes go by direction. Okay, and you need to include both of them there. Okay, so minimize, we'll start from here. So 1 to 2 minimize 30 times x12 plus then 2 to 3 50 x2 3, then 3 to 5 plus, now we'll go 3 to 5, and then we'll go 5 to 3 40 plus, then continue here 5 30 x 5 4 plus 35 x 5 6 plus, so 5 3 5 4 5 6. Okay, all done. Then 25x 6, 5. Yeah, let me just check all the ones that are included. This one, this one. Now 25 plus and the 3, 5. This one is done too. Okay, so 45x 7, 5. Okay, plus. Then I'm going to go this way. 40x 1, 4 plus 50x 7, 4 plus 50x. Okay, let's count how many arcs are there. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Did we miss something? Did we miss anyone? Okay. Let's check again. Okay, 31, 2, 50, 2, 3, 35, 3, 5, 40, 30, 35, 25, 45, 40. Okay, maybe I counted one more. Yeah, I think we covered all of them. Okay, so that's the objective function. Then let's look at the constraint. We briefly talked about the constraint just now, and we'll just start from the supply node first. Okay, so for node 1, we know there is a supply of 200 cars. Okay, so what we ship out should not exceed what we have, right? Okay, or do you remember what happened in chapter 3 in that transportation problem? Before we start to set the constraints, we check the relationship between the total supply and the total demand to see that if we are able to meet all the demands. Remember that? Okay, so in this problem, let's do a check to see the relationship between the total supply and total demand. Okay, so our total supply is 500, right? Okay, so let me erase this first. I will do the check. Okay, so it's 500 and our total demand is what? 100, 160, 230, 300, and 380. Okay, so our total demand is 380. That means we are able to fulfill all the demands. Okay, now let's set the constraints. So let me go to the next page to do this. Okay, subject 2. So for node 1, since we are able to meet all the demands, let's just set the constraint as what goes out should not exceed what we have at this node. Okay, so we have 2 outflows, so that means x12 plus x14 should be less than equal to 200. Okay, and we'll do the same for node 7, which is another supply node. Node 7. Okay, x74 plus x75 plus x76 less than equal to 300. Okay, so these are the supply node. Now I'll start from here. Then, I'll write here. Node 4, which is the only demand node. Okay, and for the demand node, because we know that the demand can be fulfilled here. So what we're going to say is that for all the cars that get shipped into this node, they need to be greater than or equal to this 80 here. Okay, so let's check what are those inflows to node 4. They are x14 plus x54 plus x74. They need to be greater than or equal to this 80 here. Okay. Then for node 2, 3, 5, 6, 7, these are the transshipment nodes. And we did some basic analysis already at the beginning. We said that for the cars that goes into this node, subtract the number of cars that goes out of this node. This should fulfill this 100 here. Okay, so node 2. That means at least 100 cars need to stay here. Okay, so x12, what goes in, minus x23, what goes out, need to be greater than or equal to 100. Okay, then for node 3, it's the same. What goes in would be x23 subtract, there is another inflow, plus x53 subtract what goes out, okay, need to be greater than or equal to the demand here. Okay, so just note that sometimes the problem probably will just give you like an arc that's bidirectional. Okay, so you know that in this kind of situation, you need to have 2 decision variables, one representing each direction. Okay, in this case, 2 arcs are given. Okay, so then for node 4, it's the demand node. Node 5. Okay, I'll ask you guys, what are the inflows? What are the inflows to node 5? You check. Okay, 3 to 5, 6 to 5, and 7 to 5, right? Okay, so x35 plus x65 plus x75 minus what goes out, x53 minus x56. Okay, what goes out, minus x54. So it has 3 inflows and 3 outflows. Need to be greater than or equal to, there's 170 here. Okay, with what we have here, can you guys write out your constraints for node 6 and 7? Oh, sorry, 7 is already done. So you only need to write out constraint for 6. Okay, so I ask you guys to write it for yourself first. By yourself first. Are you all done? Okay, if we are all done, let's write it together. So it's X inflows, right? 5 and 7. 5, 6 plus X 7, 6. 1, 2, and 1 outflow minus X 6, 5 need to be greater than or equal to 70, which is the demand here. Okay, now when you look at what we wrote, so for those transshipment nodes, it's pretty easy for us to summarize a general format for the constraint. Okay, they are, you can see here. Let me change the ink color. Okay. Okay, on the left hand side of this separation line, okay, these are all inflows to those nodes, right? And then on the right, those numbers got subtracted. These are all outflows. Okay, so with this, we can summarize a general format for the transshipment nodes constraints, which is the sum of inflows subtract the sum of outflows. Okay, and need to be greater than or equal to the demand. Okay, and let's see, can we apply this general format to this demand node? To the demand node. These are the inflows to node 4, right? So it's still inflows. And we have this subtract outflows, because the outflows of node 4 is 0. We can still write it in the same format, outflows, which is 0 in this case, right? Is greater than or equal to the demand, which is 80. Okay, so this applies to both transshipment nodes and the demand nodes. Then let's see, can we apply this to the supply node? And I'll give you a hint. To change that in the same format, we need to use a negative value to represent the supplies. Okay, so change this to negative 200. And I'll ask you to think about it to see if you can change the format of the supply nodes also to inflows minus outflows greater than or equal to a demand or the supply.